Hello class 9. Today you will watch the quick revision in basic concept of the chapter 9 circle. See student, in a circle this line is a chord and this portion on one side of the chord is called the major arc. The bigger portion, this is the major arc. On another side, this smaller portion is called the minor arc. So in this given figure, PQ is the chord and this PQ is a major arc and this side PQ is a minor arc, and this angle is subtended by the arc PQ. This angle subtended on the major arc and this angle subtended by the same chord PQ at minor arc. Now you can observe here this angle on major arc is smaller than the angle subtended on minor arc by the same chord. Now some important theorems. Theorem 9.1, equal chords of a circle subtend equal angle at the center. See, these are the equal chords, equal in length, so the measure of angle will be same. Equal chords subtend the equal angle at the center. Proof is very easy. AB and CD are two chords and these are the angles, and this triangles will prove the congruent. The very easy, radii and equal chords, it is given in the question. So by SSS, triangles are congruent. So by CPCT, these two angles are angle AOB and COD. Now see the vice versa converse. If the angles subtended by chords at the center are equal, then the chords are equal. Theorem 9.3 is also very important theorem. See, this is a chord perpendicular from the center. If perpendicular is on the chord, then it will bisect the chord. Suppose this is PQR. If it is a perpendicular, then it bisect the chord, means PR equal to RQ. Theorem 9.4 is the converse of theorem 9.3. See, it is given that the line through the center of circle bisect the chord is perpendicular to the chord. In the previous theorem, it was perpendicular, but now in this theorem 9.4, it bisects the chord. The line is not a perpendicular, a line through a center. The chord is bisecting it, then it will be perpendicular. Means if AB equal to BC, then this OBA equal to OBC equal to 90 degree. See one more basic concept. The length of perpendicular from a point to the line is the distance of the line from the point. It is given P is a point and these are the distances. This perpendicular is the shortest distance of point from the line, so say chota distance. Now see theorem 9.5, equal chords of a circle are equidistant from the center. Vice versa, the equidistant chords are equal in length. This theorem 9.6, this is the just converse. Chords equidistant from the center of a circle are equal in length. Now see example 1. If two intersecting chords of circle make equal angle with the diameter passing through the point of intersection, prove that the chords are equal. And the diameter form the equal angle with the centers. These are equal angles. Then we have to prove that these chords are equal. In triangle OLE and OME, you can see this angle is 90 degree. So this inside these are 90 degree and this OE is a common and these two angles are equal. It is given in the question. Then by AAS, these two triangles OLE and OME are congruent. These triangles are congruent by AAS, therefore CPCT, by CPCT OL equal to OE. By CPCT OL equal to OE, equidistant chords are the equal in a length. These are the equidistant because distances OL and OE are distances of the chords from the center. These distances are equal, so therefore chords are equal. AB equal to CD. We'll mention in a bracket that equidistant from the center, therefore chords are equal. Students, exercise solutions I have uploaded on my channel. You can find out in playlist class 9 maths. Among these questions, 5th and 6th are very important. Now the next topic, angle subtended by arc. See, in the previous segment we saw the angle subtended by a chord at the center. Now in this segment we will see the angle subtended by arc at the center. This is the angle subtended by chord and this is the angle subtended by arc. Now remember student, the angle subtended by minor arc is a reflex of angle subtended by major arc. This is a major arc and the total sum is 360, and suppose this is a 100, so this will be 260. Now see here student, PQ is the arc and this arc subtend this angle at the center. In the previous section we saw the chord subtend the angle at the center. In this section we will see the angle subtended by arc. So based on this concept, this theorem is very important, theorem 9.7. The angle subtended by arc at the center is twice of the angle subtended by arc at the remaining part. This we have to prove. This proof is very important. It's asked in a lot of question papers. So according to this theorem, this angle subtended by arc PQ at the center is twice of this angle. This we need to prove here. Let us join A to O and extend to B. Now see, in triangle OAP, OA equal to OP, radii. So this is isosceles triangle. Isosceles triangle means these angles are equal. Let us suppose this each is x. These angles are equal because of isosceles property. So by exterior angle property, suppose this angle is, exterior angle is 1. So angle 1 is equal to x plus x. In the similar way, see in triangle OAQ, radii, so angles are equal. Suppose these are yy and suppose this exterior is 2. So angle 2 is y plus y. So angle 2 is equal to 2y. Now let us add these two equations. Angle 1 plus this 2 LHS is equal to RHS means twice of x plus twice of y. 1 plus 2. 1 plus 2 means POQ. Is equal to twice of x plus y. 2 common. So it means twice of x plus y means PAQ. So angle POQ is equal to twice of angle PAQ. This we have to prove. Angle at the center is twice of the angle subtended by same arc in remaining part. Now the next very important property see here, angle in the same segment are equal. It means PQ is arc, angle subtended by PQ is this, angle subtended by PQ means in front of, these two angles are in front of same arc, they are covering the same arc, so they will be equal in magnitude. And the proof of this one is very easy. Angle in the same segment are equal. See, according to diagram we can write angle POQ is equal to twice of angle A. Again angle POQ is a twice of angle C. The LHS equal, so RHS will be equal. Twice of A is equal to twice of C. 2 cancel. Angle A is equal to angle C. Angle in the same segment are equal in magnitude. This theorem 9.8. And 9.9, the very simple concept is here. Points on a circle are concyclic. points on a circle are called concyclic. If we join them, this quadrilateral is called the cyclic quadrilateral. Quadrilateral whose vertices lie on the circle is called cyclic quadrilateral. 9.10, the sum of either pair of opposite angles of cyclic quadrilateral are 180 or supplementary. See, according to this theorem, cyclic quadrilateral, suppose these angles are x and y, so sum of the opposite angle is 180. In case of cyclic quadrilateral only, when the vertices lie on the circle. The converse 9.11, if the sum of pair of opposite angles are of quadrilateral are 180, then it is a cyclic. Now example 2, 3 are very important, but among these all example 2 is a very important. In example 2, it is given that a circle AB is a diameter, O is a center, and CD is a chord. This is extended to E, and given that CD chord is equal to the radius, and we had to prove that AEB is 60 degree. Angle AEB is 60 degree, and sometimes in question papers I've seen the question, it has been asked that find the angle AEB instead of proving. So angle AEB we have to find, or we can say to prove 60 degree. This we will join, these two are equal, and also we will join OD radius. So this is the equilateral triangle because radius is equal to the chord. This is the radius equal to chord 60 degree. So this angle is 60 degree. We will join here C to B also. So I use this separate color so that you should not be confused. See, I join here C to B. Now see, angle in the semicircle, one of the important concept. Angle in the semicircle, this is a semicircle, is always 90 degree. If this is a diameter and triangle around it, so this will be necessarily 90 degree right angle. So this is a right angle, so by linear pair this will also 90 degree. And see here student, just now we saw that in a theorem the angle at the center is twice of this remaining part. See, this angle in front of 60 degree, it is CD. In front of 60 degree it is arc CD, and arc CD is also in front of this angle, so this will be 30 degree. Just now we saw this theorem, the angle at the center is twice of the remaining part. It may be here or there, but they should face on the same arc. They are facing the same arc. So this is 60, so this will 30 degree. Now in triangle BCE, this angle is 90 degree. BCE plus this angle CBE 30 degree plus angle this CEB is equal to 180 by angle sum property. So this BCE is 90 degree, this one, and this is 30 degree plus CEB we have to find. So CEB is equal to 180 minus this 90 plus 30, 120, it will be 60 degree. CEB we can give the name AEB, are the same thing, 60 degree, hence proved. Example third, solution is very simple, you can see here. Now see student, example 4 is also very simple. Example 5 somehow tough, so I'll explain here, and this is very important. In example 5, it has been asked that bisectors, internal bisectors of the quadrilateral form the cyclic quadrilateral. Internal bisectors, this form this quadrilateral, it is cyclic. This we have to prove. Means sum of any two opposite pair is 180. So let us, these angles are 1 1, this 2 2, 3 3 and 4 4, because these are internal bisectors, so these pair are equal. See, coordinated property, all angles sum is 360. So it is twice of 1, twice of 2, plus twice of 3, and twice of 4 is 360. So 1, 2, 3, 4 is 180. Divided by 2, it will be 180. Now, in triangle AHD, angle 1 plus this H plus this 1, this H plus this 4, 180. Similarly, in triangle BFC, angle 2, 3 and F is 180. I will add these two, 1 plus 2 plus 3 plus 4, and H and F is 360, 180, 180, 360. But 1, 2, 3, 4, we already proved 180. So instead of this 1, 2, 3, 4, we will write 180. So H plus F will be 180. So it is a cyclic quadrilateral EFGH. All solutions I have been uploaded on my channel. In playlist you can find out class 9th maths. But some important question we do here, like question number 2 is very important. Diagram is not given. In the question it is said that a chord of circle is equal to the radius. A chord of circle equal to its radius. Suppose this is AB. Find the angle subtended by chord point on minor and major arc. This chord is subtending angle here in the minor arc and this in major arc. Suppose this is P and this is Q. You have to find the angle P and Q. See, whenever you will see the chord is equal to radius, we saw in the previous some question examples, chord is equal to the radius. So it means this radius is also equal to chord. This is an equilateral triangle. So these all three angles are 60 degree. Now using that theorem, angle at the center is twice of the remaining part. This is at the center and this is at the remaining part. So this will be 30 degree facing the same arc AB. So this is 30 degree. Very simple. You have to mention only theorem that the angle subtended by R at the center is twice of the angle subtended by arc, same arc at the remaining part. So this is 60, so this will be half 30. Now see, in a cyclic quadrilateral APBQ, in a cyclic quadrilateral APBQ, the sum of opposite angle is 90 degree or 180 degree, supplementary. Cyclic quadrilateral properties, sum of the opposite angles are 180. So Q 30 we calculated here. So it is 180. So angle P will be 150. This is 30 degree and this P is 150. P means angle subtended at minor arc. And Q means angle subtended major arc. So always remember here, at the major arc the angle is smaller and at the minor arc angle is bigger. Now question 3rd is also important. See in a diagram, it is given that angle PQR is 100 degree. This is 100 degree. We have to find the angle OPR. This angle we have to find. See, very simple. Angle at the center is twice of remaining part, so this angle will be 200 because this is at the center. It is center, and the reflex angle inside this will be 160. Let us see clearly in a diagram. At remaining part is 100, so angle at the center will be 200. And the reflex angle because this is the center, so angle on opposite side will be 160, and the radii are equal. So these angles will be equal. Let us suppose XX. So angle X plus angle X plus 160, 180 in a triangle. 2x is 180 minus 160. So x is equal to 10 degree. In this triangle we use the angle sum property. Angle OPR will be 10 degree. This question 4 is also very important. It is given ABC 69 and ACB 31. We have to find BDC. See, using the angle sum property, you will find this angle. Angle A plus 69 plus angle 31 is 180. Angle A will be 80 degree. Now see angle in the same segment. We saw the property. Angle in the same segment means angle subtended by same arc. They are facing the same arc, so they are equal in magnitude. So A is 80. So this BDC will also 80 degree. So rest of the questions are easy. You can do and find out and try to solve. If you are having any doubt, you can write in the comment box. Let us see here. Next page, just this one, 9th is also very important. So we have to do here. See, it seems to be very tough question, but it is very easy. Two circles intersect at B and C. Very simple. ABD, PBQ is line segments, and we have to prove that ACP equal to QCD. ACP, this angle, we have to prove that equal to QCD. See students, if your basic concepts are clear and every theorem you go through, then you can do any question, any harder question. Focus on the diagram, student. Angle ACP in a bigger circle and this angle, suppose this angle is 1, are equal. Angle in the same segment because they are facing the same arc AP. Similarly, in a smaller circle, angle QCD, this angle QCD and this angle, suppose this is 2, are equal. They are facing the same arc DQ, angle in the same segment. So we will write here angle QCD equal to angle 2. But angle 1 and 2 are equal because they are vertically opposite angle. So this RHS equal 1 equal to 2. So LHS will also equal. Therefore, hence prove that ACP equal to QCD. Very simple.